Hello everyone, in this lecture I will solve different problems in linear momentum and collisions. So let's start here. A 2000 kilogram truck traveling at speed of 6 meters per second makes a 90-degree turn in a time of 4 seconds and emerges from this turn with speed 4 meters per second. What is the magnitude of the average resultant force on the truck during this turn? Now to solve this one here, let's find Fx average, which equal to delta P over delta T. Now delta P over delta P, P final, Px final minus Px initial divided by delta T, or equal to M times Vx final minus Vx initial over T final minus T initial. So Fx average will be equal to, the mass is 2000 times Vx final, because it turns and making 90-degree, so x final here equal to 0 minus the x initial, it's 6. The time interval for this one here, it's 4. So this one here equal to minus 3000 newtons. Again, let's find Fy average, which equal to delta P over delta T, or mass V final Y minus V initial Y divided by delta T, which is T final minus T initial. Now you substitute the numbers, 2000 times, now V final initial, this one here, it's equal to 0, and the final Y equal to 4 divided by 4. After all, it's equal to 2000 Newton. Now F here, it's equal to square root of Fx square plus Fy square, or equal to square root of 3000 minus, it doesn't matter actually the minus because it's a square, plus 2000 square. So F in this case here equal to 3600 Newton. A 1.2 kilogram object moving with a speed of 8 meters per second collides perpendicularly with a wall and emerges with a speed of 6 meters per second in the opposite direction. If the object is in contact with the wall for 2 milliseconds, what is the magnitude of the average force on the object by the wall? Now let's just represent the situation here. This object collides with the wall with velocity equal to 8 meters per second. Now bounces back with velocity equal to 6 meters per second, and the contact time delta T here, it's equal to 2 milliseconds. Now to find the impulse in this one here, impulse is actually equal to the net force, that's what we're looking for, delta T. Now the net force, it's equal to the impulse, in this case it's P final minus P initial over delta T, or the mass of the object times the velocity. The final velocity, it's actually 6 minus, now the initial velocity, it's 8, but since the initial velocity is going this way and this one going this way, so minus 8 in this case here, divided by 2 10 to the power minus 3, 2 milliseconds, and the net force after all will be equal to 1.2 times 14 divided by 2, 10 to the power minus 3, or 8.4 10 to the power 3 newtons. A 1.5 kilogram playground ball is moving with a velocity of 3 meters per second, directed 30 degrees below the horizontal. Just before it strikes a horizontal surface, the ball leaves this surface 0.5 seconds later with a velocity of 2 meters per second, directed 60 degrees above the horizontal. What is the magnitude of the average resultant force on the ball? Let's grab the situation. Now, assuming that this is the horizontal, now the ball is fired 30 degrees below the horizontal now and bounces back with 60 degrees above the horizontal. And this one here, the velocity 2 meters per second, and the contact time equal to 0.5 seconds. Now we need to find the magnitude of the average resultant force on the ball. Since this is a two-dimensional problem and momentum is a vector quantity, there is momentum on x and momentum on y. So let's calculate the change in momentum at x. Delta p x equal to p final x minus p initial x, and equal to, remember, momentum equal to mv, so the mass is 1.5 times vx, the final x. Now we have to analyze this one here, is 2 cosine 60, like this one here, 2 cosine 60, this one, minus 1.5 times the initial one, if this is like this one here, is this like here, equal to 3 cosine 330. And remember, the angle is measured from positive x-axis counterclockwise, so we have to measure the angle like this one here. It's 330, and in this case delta px equal to, or the change in momentum at x equal to this one here, 1.5 minus 3.9, or after all it's equal to minus 2.4 kilogram meter per seconds. Now let's follow the same procedure when calculating the change in momentum at y equal to p final y minus p initial y, and from this one here, so the mass is 1.5 times p final y, this one here on the y-axis, so it will be 2 sine 60 minus p initial y, this one here. If this is the x-axis here, the y-axis will be this one here, and it will be 3 sine 30. So 1.5, 3 sine 30. And remember, the direction of the arrow will be downward in this case, so it will be minus, so minus minus will be plus. After simplifying this one here, it's equal to 2.6 plus 2.25, or 4.85 kilogram meter per second. Now, sum of all forces on x equal to, now on x it's delta px, divided by the time interval, which is in this case equal to 0.5, so it's equal to 4.8 newtons with minus sign, and sum of all forces on y equal to 9.7, which is delta P, 4.85 divided by 0.5. Now F in this case will be equal to square root of fx square, 4.8 square with minus sign, plus 9.7 square. You simplify this one here, F will be equal to almost 11 newtons. The only force acting on a 2 kilogram object moving along the x-axis is represented right here. If the velocity Vx is equal to minus 2 meters per second at t equal to 0, what is the velocity at t equal to 4 seconds? Now we would like to find the velocity at 4 seconds. Now at 4 seconds has to be somewhere this one here. Now as we can see here, if we chop this graph into non-graphs, so this one here, the first piece, second piece, and third piece. Now the area beneath this one right here, it's a rectangle. Now this rectangle here is equal to the width times the length. Now the length is F, the net force, and the width is delta T. So F delta T is equal to the area beneath the curve. For this one here, it's a rectangle again, and it's equal to the width, which is in this case 1, and the length, which is in this case 4. So the area for the first one is 4. Now for the second one, it's a triangle, and remember the triangle, it's half the base. The base in this case, it's equal to 1, and the height is 4. So half times 4 times 1 is the base. After all, it will be equal to 2. Now the third part, this one here, is another triangle, and the area for this triangle, it's equal to half, the third part, half. The base for this one here, it's equal to 2, and times the height for this one, it's minus 8. After all, it will be equal to minus 8. Now the total area for this one here, it's equal to 4 plus 2 minus 8, and this whole thing is equal to sum of all forces delta T, this equal to minus 2. Remember, sum of all forces delta T, it's equal to P final minus P initial, or equal to M V final, that's what we are looking for, minus 2 is the mass, times the velocity at t equal to 0, it's equal to minus 2. You simplify this one here, it's equal to 2 V final plus 4 equal to, now F delta T, we just calculated this one, it's equal to minus 2. And V final will be equal to minus 2 minus 4 divided by 2, which is equal to minus 3 meter per second. A 3 kilogram ball with an initial velocity 4I plus 3J meter per second collides with a wall and rebounds with a velocity minus 4I plus 3j meter per second. What is the impulse exerted on the ball by the wall? Now let's just sketch the situation. A ball collides with the wall with velocity equal to 4I plus 3j and rebound like this one here with velocity minus 4I plus 3j. Now we would like to calculate here the impulse. Remember, impulse j, it's equal to delta p, and since delta p is a vector quantity, we have to analyze p into x and y components. So impulse actually on x equal to p final x minus p initial x. Now the mass of the object equal to 3 times final x velocity, which is minus 4 minus 3 times the initial velocity, it's 4 in this case here, so it's equal to 3 times minus 8, or the impulse on x, it's equal to minus 24 Newton second. Now the impulse on y equal to delta py, or the mass is equal to 3 times the final velocity on y, it's just 3 minus 3. The initial velocity, it's equal to 3. So the impulse on y equal to 0. So the impulse is actually just impulse on x, which equal to minus 24 Newton second. A 2.4 kilogram ball falling vertically hits the floor with a speed of 2.5 meter per second and rebounds with a speed of 1.5 meter per second. What is the magnitude of the impulse exerted on the ball by the floor? Now here's the ball, this one here, falls and hits the ground with velocity equal to 2.5 meter per second and rebound with velocity equal to 1.5 meter per second. Now the question is, what is the impulse? Now impulse here, it's equal to delta, the change in momentum. We have here just one-dimensional motion on the y-axis, so delta p y in this case, or m the final minus m the initial. The mass is equal to 2.4 times 1.5, this is the final velocity right here, minus, now the mass again, it's 2.4 times the velocity here, it's minus 2.5 because it's going down, minus 2.5. You simplify this one here, it's equal to 3.6 plus 6, or the impulse is actually equal to 9.6 Newton seconds, or you can say kilogram meter per second. An 8 kilogram object moving 4 meter per second in the positive x direction, which has one-dimensional collision with 2 kilogram object moving 3 meter per second in the opposite direction. So the final velocity of the 8 kilogram object is 2 meter per second in the positive x direction. What is the total kinetic energy of the two-mass system after the collision? So here is the situation. We have an object right here moving this way with velocity equal to 4 meter per second, and the mass for this one here, it's 8 kilograms. And another object, this one here, is moving this way with velocity equal to 3 meters per second, and the mass for this one here, it's 2 kilogram. When they collide, the system is moving in the positive x direction with velocity equal to 2 meters per second. The question, what is the total kinetic energy of the two mass system after the collision? Now in this situation, momentum is conserved, so let's name it this one 1 and this is 2. M1 V1 initial plus M2 V2 initial is actually equal to M1 V1 final plus M2 V2 final. You substitute the numbers. 8 times 2, 32 minus 6 equal to 16 plus 2 V2 final. You simplify this one here, you will find V2 final equal to 5 meters per second. Now the total kinetic energy of the two mass system after the collision. So we need actually the total kinetic energy for both systems here. So K final equal to K initial or K1 plus K2. After all, K1 is the final kinetic energy for the 8 kilogram object, and K2 is the final kinetic energy of the 2 kilogram object. So half 8, and the velocity, the final velocity for the 8 kilogram object, it's 2 square plus half 2. 5 square, we just calculated this one here, 25. You simplify this one here, the total kinetic energy of the two masses after the collision, it's equal to 16 plus 25 or 41 joules. A 1.6 kilogram ball is attached to the end of 0.4 meter string to form a pendulum. This pendulum is released from rest with the string horizontal. At the lowest point of its swing, when it's moving horizontally, the ball collides with 0.8 kilogram block initially at rest on horizontal frictionless surface. The speed of the block just after the collision is equal to 3 meters per second. What is the speed of the ball just after the collision? Here's the situation. We have an object like this one here and another object located somewhere right here. Now this object collides, freely released on this one, and collide with this block here, which is initially at rest. We would like to calculate the speed of the block just after the collision, assuming that the speed of the block just after the collision is equal to 3 meters per second. We would like to calculate the speed of the ball just after the collision. Since there is no air resistance, no friction whatsoever, in this case we can use initial equal to E final, the simplified form of work energy theorem. And at this position, this ball maintains just potential energy. So M, G, H, no kinetic energy at this position. Now, at this position, this is the final position, this one here. At this position, the ball maintains a kinetic energy and no potential energy, assuming that this is the ground level. So half M V final square. Mass cancel out with mass, and V in this case will be equal to square root of 2 g h. With numbers, it's equal to 2, g is 10, and h is this one here, is the same as this, by the way, so it's equal to 0.4. After all, it's equal to 2.8 meter per second. So this is the speed of the ball just before the collision. Now we would like to calculate the speed of the ball just after the collision in this situation. Now let's do this. Momentum in this case is conserved, and let's name them here. M for the block, let's name it 2, and this one. M2 V2 initial plus M1 V1 initial equal to M2 V2 final plus M1 V1 final. Remember, 1 is the ball, 2 is the block. Now, the block initially at rest, which means this one here equal to 0. M1, the mass for the ball, it's 1.6 times. Now the initial velocity of the ball is actually the final velocity of the first stage, assuming that this is the first stage and this is the second stage. So it's equal to 2.8, we just calculated that one here, equal to mass for the block, it's equal to 0.8 kilogram times the velocity of the block, it's equal to 3, plus M1, it's 1.6 times V1 final. That's what we are looking for. The speed of the ball after the collision. Upon simplifying this one here, V1 final will be equal to 1.3 meter per second. A 2 kilogram object moving with a velocity of 5 meters per second in the positive x direction strikes and sticks to a 3 kilogram object moving with a speed of 2 meters per second in the same direction. How much kinetic energy is lost in this collision? Now here's the situation. We have an object, let's name it 1, and with mass equal to 2 kilogram, velocity 5 meters per second, moving in the positive x direction, and strikes another object here, mass equal to 3 kilogram, and moving in the same direction this way here with a speed equal to 2 meters per second. Now, both objects after the collision stick together, which means this collision is completely an elastic collision. The question is, how much kinetic energy is lost in this collision? Since this is an elastic collision, only the momentum is conserved and kinetic energy is not conserved. And this again, this is one-dimensional collision. In this case, M for the first object, V for the first object initial, plus M for the second object, V2 initial for the second object, it's equal to, since they are stick together, so M1 plus M2 times V final. No need here to name it 1 or 2 because it's the same speed for both objects when they stick together. Now you substitute the numbers. Now 2 times 5 plus 3 times 2, this actually equal to, the masses is 2 plus 3, which is 5, V final. After all, V final will be equal to 16 over 5 or equal to 3.2 meter per second. Let's calculate the kinetic energy before the collision and calculate the kinetic energy after the collision. And again, they shouldn't be the same because it's inelastic collision and kinetic energy is not conserved. So kinetic energy before the collision, it's equal to K1 plus K2 and half M1 V1 initial square plus half M2 V2 initial square. You substitute the numbers here, you will find KB before equal to half 225 plus half 3 4, or in other words, it's equal to 31 joules. Now, kinetic energy after the collision equal to half M1 plus M2 V final square. You substitute this one here, half 5, it's 3 plus 2 times the final velocity. We just calculated this one here. It's equal to 3.2 meter per second square. After all, it's equal to 25.6 joule. Now the last in kinetic energy, it's delta K. For this one here, it's equal to 5.4 joule, which is the difference between the kinetic energy before and kinetic energy after. A 12-gram bullet moving horizontally strikes and remains in a 3-kilogram block initially at rest on the edge of a table. The block, which is initially 80 centimeters above the floor, strikes the floor horizontal distance of 120 centimeters from its initial position. What was the initial speed of the bullet? Now here's the situation. We have here an object and a bullet hits this object and is stuck inside it. Now this whole system here moves as a projectile with horizontal distance 120 meters, assuming that the height of this desk or table it's 80 centimeters, this one here, and again assuming that this is the reference point right here. So y here it's equal to 0. Now we would like to calculate the initial speed of the bullet. To do this, let's use equations of motion. Y final equal to y initial plus the initial y t minus half g t square. Y initial it's 0 and the initial velocity it's actually 0 as well in this one here. So y final it's 0.8 equal to half g, it's equal to 10 t square, and don't forget the minus here, and y final is actually minus 0.8 because it's below the reference point. So minus with minus, it's just a plus, and from this one we can extract or calculate the time t, which equal to square root of 0.16, or in other words 0.4 seconds. Now let's implement the time here in the x equation. So x final here equal to x initial plus the initial x t. Now again, x initial equal to 0 and x final, it's just mentioned here, it's 1.2 meters. It has to be in meters, this centimeter. So it has to be in meters, 1.2 meters equal to the initial x times the time here, it's 0.4 seconds. After all, the initial x, it's equal to 3 meter per second. Since this is a projectile motion, velocity on x is constant. In this case here, let's use P final equal to P initial, or in other words, the mass for the bullet, which is 0.012, plus the mass for the block, which is 3 in this case, times V final here equal to M for the bullet, V for the bullet initial, plus M for the piece of wood, V for wood. Now the block initially at rest, so this one will be equal to 0, and V final here is actually equal to V initial because on x the velocity is constant, and in this case V bullet initial equal to 0.012 plus 3 times 3 divided by 0.012. In this case, the initial velocity of the bullet is equal to 753 meter per second, or 0.75 kilometer per second. A 6 kilogram object moving 5 meters per second collides with and sticks to 2 kilogram object. After the collision, the composite object is moving 2 meters per second in a direction opposite to the initial direction of motion of the 6 kilogram object. Determine the speed of the 2 kilogram object before the collision. Since the objects stick together, in this case here, it's inelastic collision, so only the momentum is conserved. So P initial equal to P final. Now P initial is the M1 V1 initial plus M2 V2 initial equal to M1 plus M2, again they are stick together, V final. Now 6 times 5 plus 2 times V2 equal to 6 plus 2 times, now remember, both objects, when they stick together, they are moved with the speed in opposite direction, so it will be minus 2. You simplify this one here, V2, it's equal to 46 over 2, or 23 meter per second. A 2 kilogram object moving 5 meters per second collides with and sticks to an 8 kilogram object initially at rest. Determine the kinetic energy lost by the system as a result of this collision. Now, since they stick together, kinetic energy is not conserved. In this case, P initial equal to P final, but K initial is not equal to K final. So M1 V1 initial plus M2 V2 initial equal to M1 plus M2 V final. So 2 times 5 plus 8 times 0 equal to 2 plus 8 V final. Simplify this one here. So V final will be equal to 1 meter per second. Now the kinetic energy or the initial kinetic energy, it's equal to the initial kinetic energy for the first object and the initial kinetic energy for the second object. And the second object is initially at rest, so there is no kinetic energy for the second object. So it's half 2 times V squared, it's 5 squared, 25, plus 0, or 25 joules. Now the final kinetic energy, it's equal to half the total mass, it's equal to 80 plus 2 times V final. We just calculated this one right here. So 1 square, so it's equal to 5 joule. Now the last kinetic energy equal to subtract this one from this one here, it's equal to 20 joule. A 3 kilogram mass sliding on a frictionless surface and has a velocity of 5 meters per second east when it undergoes a one-dimensional inelastic collision with 2 kilogram mass that has an initial velocity 2 meters per second west. After the collision, the 3 kilogram mass has a velocity of 1 meter per second east. How much kinetic energy does the two mass system lose during the collision? Here's the situation. We have one object is moving east and velocity here equal to 5 meters per second, and another object is moving west this way with velocity is 2 meters per second. The mass for this one, it's equal to 3, and the mass for this one, it's equal to 2. In this case, momentum is conserved, so m1 v1 initial plus m2 v2 initial equal to m1 v1 final plus m2 v2 final. Substitute numbers here, so 3 times 5 plus 2. Now v21, since it's going to the west, so it's minus 2, equal to 3 times 1 plus 2 v2 final. So from this one here, v2 final is equal to 4 meters per second. The initial kinetic energy, it's equal to half m for the first one, it's 3, and v square, it's 5 square, so 25, plus half m for the second object, it's 2, times the speed for the second object, it's 2 square, which is 4, and in this case you do this, you will find K initial, or the kinetic energy, or the initial kinetic energy, it's equal to 41.5 joule. Now the final kinetic energy, it's equal to half 3 times the final velocity for the first object, it's 1 meter per second, plus half 2, and we just calculated the final velocity for the second object, which is 4 square is 16. After all, K final equal to 17.5 joule. So the loss in kinetic energy equal to 17.5 minus 41.5, or equal to 24 joules. And the minus sign, it means lost energy. A 3 kilogram mass is released from rest at point A, right here, of a circular frictionless track of radius 0.4 meter. As shown in the figure, the mass slides down the track and collides with 1.4 kilogram mass that is initially at rest on horizontal frictionless surface. If the masses stick together, what is their speed after the collision? Now, to solve this one here, again, this is inelastic collision, kinetic energy is not conserved. So P initial equal to P final M1 V1, let's name them MA VA initial plus MB VB initial equal to MA plus MB V final. Now V final here is missing. We need to calculate this one here. Now let's use the simplified form of work energy theorem. So E initial equal to E final, and at this position right here there is only potential energy because it has some height from the ground level, so this is y equal to 0. So mgh equal, now at this position right here it has kinetic energy and no potential energy whatsoever, so half mv final square, and mass with mass, so V final before the collision, it's equal to, in this case, square root of 2gh, or square root of 2 times 10, and h in this case it's 0.4, so V will be equal to 2.83 meter per second. Now assuming that this is the first stage here and the collision is the second stage, the final velocity in the first stage is actually the initial velocity of the 3 kilogram object. Back to this equation right here, the second object initially at rest, so this will be 0. Now VA initial is actually the final velocity for the first stage, so MA, which is a 3 times 2.83 equal to 3 plus 1.4 V final. You simplify this one here, V final equal to 1.93 meter per second. A 3 kilogram mass is sliding on horizontal frictionless surface with a speed of 3 meters per second when it collides with 1 kilogram mass initially at rest as shown in the figure. The masses stick together and slide up a frictionless circular track of radius 0.4 meter. To what maximum height h above the horizontal surface will the masses slide? Now this situation is opposite to the other one. Now we have here both systems, they stick together and move up to the maximum height. Again, we have here two situations, a collision and energy conservation. So let's calculate the maximum height. Now momentum is conserved, so M1, it's named MA, VA initial plus MB, VB initial. Now this one A and this is B, equal to M1 plus M2 V final Now this one initially at rest, so the 3 kilogram mass with speed equal to 3 equal to 3 plus 1, which is 4, V final. From this one here, V final will be equal to 9 over 4 meter per second, or V final equal to 2.25 meter per second. Now E final equal to E initial. Again, we use this rule because there is no friction on the track, and E final, this is the final position right here, it's equal to mgh. And remember, m here is the total mass, which is ma plus mb. But in this case, it doesn't matter because it cancels out. So equal to E initial, it's just kinetic energy, half mv initial square. So mass cancel out with mass. Now initial for the second stage is actually the final for the first stage, and in this case V initial equal to V final, or 2.25 meter per second. You substitute this one here, you will find H equal to V final square divided by 2g, or 225 square divided by 20, and after all the maximum height will be equal to 0.25 meter. A 10-gram bullet moving horizontally with a speed of 2 kilograms per second strikes and passes through a 4 kilogram block moving with a speed of 4.2 meters per second in the opposite direction. On a horizontal frictionless surface, if the block is brought to rest by the collision, what is the kinetic energy of the bullet as it emerges from the block? So we have here in this situation a bullet moving with speed equal to 2 kilometers per second collides with a block moving in the opposite direction with speed equal to 4.2 meter per second. Now the bullet is passed through the block here, and the block is brought to rest. The question is, what is the kinetic energy of the bullet as it emerges from the block? Now, assuming that this is system 1 and this is 2, this one here, so momentum is conserved, which means m1 v1 initial plus m2 v2 initial equal to m1 v1 final plus m2 v2 final. And as mentioned in the question, the block after the collision brought to rest, so this one will be equal to 0. When we substitute the numbers, m1 it's 10 grams, it has to be in kilograms, so it's 0.01 times the speed is 2 kilometers per second, and it has to be in meters per second, or 2000 meter per second, plus m2 it's 4, and v2 initial it's 4.2, but it's moving in the opposite direction, this way right here, so it has to be minus 4.2 meter per second. This equal to 0.01 the mass for the bullet, v1 final, and from this one here v1 final will be equal to 320 meter per second. Now the kinetic energy will be equal to half because we look for the kinetic energy of the bullet as it emerges from the block. Half, and the mass, it's 0.01 times 320 square. After all, it's equal to 512 joules. A 3 kilogram object moving in the positive x direction and has one-dimensional elastic collision with 5 kilogram object initially at rest. After the collision, the 5 kilogram object has a velocity 6 meters per second in the positive x direction. What was the initial speed of the 3 kilogram object? And here's the situation. We have a 3 kilogram object moving with unknown speed and another object with mass equal to 5 kilogram initially at rest. Now, after the collision, the 5 kilogram object has velocity equal to 6 meters per second in the positive x direction. Now we need to calculate the initial speed of the 3 kilogram object. Now, this collision is elastic collision, and the kinetic energy is conserved and the momentum is conserved as well. For this type of collision, let's use the ready equations from solving the kinetic energy and momentum energy. So V1 final equal to m1 minus m2 divided by m1 plus m2 V1 initial plus 2m2 m1 plus m2 V2 initial, and V2 final, the final velocity for the second object, it's 2m1 m1 plus m2 V1 initial plus m2 minus m1 over m1 plus m2 V2 initial. And remember, these two equations extracted from conservation of momentum and conservation of kinetic energy. And because this is the elastic collision, we can just use these ready equations. Now, what was the initial speed of the 3 kilogram object? Now let's simplify these two equations. The second object, this is block here, initially at rest, so the initial velocity equal to 0, and this part is equal to 0 as well. Now, the initial speed of the 3 kilogram object, let's use this part here, this one here. The final velocity for the block equal to 6 to m1, it's just 3 divided by 3 plus 5 times V1 initial, and from this one here, V1 initial, or the initial speed of the 3 kilogram object, it's equal to 8 meters per second. A 3 kilogram object moving 8 meters per second in the positive x direction and has a one-dimensional elastic collision with an object with mass equal to m initially at rest. After the collision, the object of unknown mass has a velocity 6 meters per second in the positive x direction. What is the mass m? Now again, to solve this one here, this is elastic collision and kinetic energy is conserved and momentum is conserved. We can just simply use the previous equations in the previous example. I will just copy them right here. Now, the initial velocity for the mass m is 0, and this will be equal to 0. Now again, 6 equal to 2 times 3, I'll use this part here, divided by m1, it's 3 plus capital M, that's what we're looking for, times an initial, it's 8, and from this one here, 3 plus M equal to 8, or M equal to 5 kilograms. A 2 kilogram object moving 3 meters per second strikes a 1 kilogram object initially at rest. Immediately after the collision, the 2 kilogram object has a velocity of 1.5 meters per second directed 30 degrees from its initial direction of motion. What is the x component of the velocity of the 1 kilogram object just after the collision? Here's the situation. We have an object, 2 kilogram object is moving with 3 meters per second, strikes a 1 kilogram object initially at rest. Now, after the collision, the 2 kilogram object, this one here, moves with speed equal to 1.5 meters per second and directed with 30 degrees with the horizontal. So this one here, the 2 kilogram object. We would like to find the x component of the velocity of the 1 kilogram object after the collision. So we need to find Vx for this one right here. Now, since it's asked about the x component, in this case now I need to find the momentum y components. So in this one here, P initial x equal to P final x, or M1 V1 initial plus M2 V2 initial equal to M1 V1 final plus M2 V2 final. In this case, 2 times 3 plus, now this one here is 0 because the object initially at rest, equal to, now M1 it's 2, V1 final is actually the x component for the V1, which is 1.5 cosine theory. Plus M2, in this case it's just 1, times V2 final, that's what we are trying to find. So 6 equal to 3 cosine theory plus V2 final, and from this one here, V2 final is actually x because it's x component, equal to 3.4 meters per second. A 6 kilogram object initially at rest in free space explodes into 3 segments of equal mass. 2 of these segments are observed to be moving with equal speeds of 20 meters per second with an angle 60 degrees between their directions of motion. How much kinetic energy is released in this explosion? Now let's see here. A 6 kilogram object, this one here, split into 3 pieces like this. So 1, 2, and 3. Masses of these 3 pieces is the same, and the angle between the 2 of them is 60 degrees. Now in this case, we would like to find how much energy is released from this explosion. Now let's calculate. K, or the kinetic energy, is equal to half M1 V1 square plus half M2 V2 square plus half M3 V3 square. Remember, they split into 3 equal pieces. So M1 equal to m2, which is equal to m3, and let's name it m. And k in this case will be equal to half just m times v1 square plus v2 square plus v3 square. Now the question is, we need to calculate v1, v2, and v3, and let's use the information given in the question here. P final x equal m1 v1 plus m2 v2 plus m3 v3, and P final x for this one here equal to P initial x. Now P initial x is actually equal to 0. Now from this one here, it's equal to m times 20 cosine. Now the 60 here is between these two masses, and if we set the horizontal to be right in the middle between them, so the angle will be 30 plus 20 cosine 30 plus v3, which is missing in this case, all this equal to 0, and from this one here, v3x equal to minus 34.6 meter per second. Now let's follow the same procedure. P final y equal to m20 sine the y components 30 plus 20 sine 30 plus v3y, this v3x by the way, and this whole thing equal to 0. Now the situation here is quite different, because the y component for this one here, it's in the positive direction, while the y component for this one, it's in the negative. So this will cancel out with this, and in this case v3y equal to 0. Now the kinetic energy equal to, let's use just this one here, half m. In this case it's 2, because 6 kilogram split into 3 equal pieces, so each piece has a mass equal to 2 kilograms, times (20) square plus 20 square plus 34.6. Negative here doesn't matter because it's a square, this one here, or 400 plus 400 plus 1197. In total, the kinetic energy, or the released kinetic energy, it's equal to 1997.2 joule. A 5-gram particle moving 60 meters per second collides with a 2-gram particle initially at rest. After the collision, each of the particles has a velocity that is directed 30 degrees from the original direction of motion of the 5-gram particle. What is the speed of the 2-gram particle after the collision? Now again, we have here an object collide with another object here, and one object moves making 30 degrees with the horizontal, and the other object, this is 1 and this is 2, this is 1 and this is 2, making 30 degrees with the horizontal as well. Now we would like to calculate the speed of the 2 kilogram object, this one here. Now to solve this one here, let's find P initial x equal to P final x. So M1 V1x plus M2 V2x equal to M1 V1 final plus M2 V2 final. This one will be equal to 0. Now we substitute the numbers. So 0.005, it has to be in kilograms, times 60 equal to 0.005 the final one cosine theory plus 0.002 the other object, the final 2 cosine theory. This one here, when you analyze this one, the x component and the x component. And upon simplifying this one here, 0.3 divided by cosine theory equal to 0.005 the final one plus 0.002 the final 2. Let's keep this equation here. Now from the y component of the momentum, P initial y equal to P final y, and from this one here, there is no y component before the collision, so 0 equal to 0.005 the final one sine theory. Now it has to be plus, but the y component for the second particle, it's in the negative direction, so minus 0.002 the final 2 sine theory. So from this one here, we can find that the final one equal to 0.002 divided by 0.005 the final 2. Now if we substitute this one here back in this equation right here, you will get 0.3 divided by 0.87 equal to 0.005 times 0.002 divided by 0.005 the final 2 plus 0.002 the final 2. This cancels out with this, and from this one here you will get the final 2 equal to 85 meter per second, which is the speed of the second particle. If we would like to find the speed of the first particle, we can just substitute this V2 final with this one here. You will get V final 1 equal to 34 meter per second. A 1 kilogram object moving 9 meters per second collides with 2 kilogram object moving 6 meters per second in a direction that is perpendicular to the initial direction of motion of the 1 kilogram object. The two masses remain together after the collision, and this composite object then collides with and sticks to a 3 kilogram object. After these collisions, the final composite, which is 6 kilogram in this case here, object remains at rest. What was the speed of 3 kilogram object before the collision? Now here's the situation. We have one object moving this way here, 1 kilogram, with speed equal to 9 meters per second. Another object moving this way here in the y direction, and the mass for this one here, it's 2 kilogram, and the speed is 6 meter per second. Now they collide together and stick. After they collide and stick together, it collides with another object, this one right here. The question, we need to calculate the speed of the 3 kilogram object before the collision, this one here. Now we have here two collisions. Now the first one, the first collision here, now let's use momentum is conserved. Remember, this is an elastic collision, so no kinetic energy, or kinetic energy is not conserved, only momentum. So M1, let's name them 1, 2, and this is 3. M1 V1 initial plus M2 V2 initial equal to M1 plus M2 V final x, because P initial x equal to P final x. Now this is x and this x. Now the second object, which is this one here, it has no x component for the speed, and from this one here, the final x equal to 1 times 9 divided by 3, or equal to 3 meter per second. Now from the y component of momentum, M1 V1 initial y plus M2 V2 initial y equal to M1 plus M2 V final y. Again, this one here is equal to 0, because in the y component, the object number 1 has no y component here, and you simplify this one here, the final y equal to 2 times 6 over 3, or equal to 4 meter per second. Now final speed here, it's equal to square root of 3 square plus 4 square, or 5 meter per second. Now this is the final velocity for the first wreckage. Now this object, the whole object here, collides with another object moving with some velocity, we don't know how much, and after the collision, the whole thing remains or brought to rest. Now collision 2, in this one here, the total mass V1 initial plus M3 V3 initial equal to M plus M3 V final. Since the whole wreckage brought to rest, so this will be equal to 0. M here is the mass for object 1 and object 2. So 1 plus 2, it's 3. The initial velocity for the second case is actually the final velocity for the first case, times 5, plus mass for object 3, it's equal to 3 times, or V3 initial, this whole thing equal to 0. Upon simplifying this, V3 initial will be equal to minus 5 meter per second. A 3 kilogram mass sliding on a frictionless surface explodes into 3 1 kilogram masses. After the explosion, the velocities of the 3 masses are, for the first one, it's 9 meter per second and going north. The second one, it's 4 meter per second and making 30 degrees south of west. And the third piece has a speed equal to 4 meters per second and making 30 degrees south of east. Now, what was the magnitude of the original velocity of the 3 kilogram mass? Now, here's the situation. We have an object. This object here explodes into 3 pieces, one and this x and y, like this one here, and one like this one here, making 30 degrees south of west with speed equal to 4 meters per second, and this one right here making 30 degrees 4 meters per second, and this one going to north with 9 meters per second. Now, in this case here, we would like to calculate the magnitude of the original velocity of the 3 kilogram mass. Now, P initial x equal to P final x. And in this case, P initial y equal to P final y. So, M Vx equal to M1 V1x plus M2 V2x plus M3 V3x. Now, if we look at this one here, M1, it has no x component, so this one will be 0. Now, the mass here, the total mass, it's 3 Vx, which is the original speed for the 3 kilogram mass, equal to M2, it's 1, the mass, it's 1, V2x, which is in this case minus 4 cosine 30. Now this one here, the x component, which is minus 4 cosine 30 plus 1 4 cosine 30. And you do this, you will find Vx equal to 0. Now let's follow the same procedure for the y component of the speed, which is m in this case Vy equal to m1 V1y plus m2 V2y plus m3 V3y, and you substitute m1, which is 1 V1y 9 plus 1 minus 4 sine 30 plus 1 minus 4 sine 30, because the y component for this one here, it's negative, and the y component for this one here is negative as well. So 3 Vy equal to 9 minus 2 or 5, and from this one here Vy equal to 5 over 3 meter per second. Now V will be equal to square root of 0 square plus Vy square, or 5 over 3. In other words, it's equal to V equal to 1.66 meter per second. A 5 kilogram mass with an initial velocity of 4 meters per second east collides with a 4 kilogram mass with an initial velocity of 3 meters per second west. After the collision, the 5 kilogram mass has a velocity of 1.2 meters per second south. What is the magnitude of the velocity of the 4 kilogram mass after the collision? Now we have here one object right here, 5 kilogram, and another object which is 4 kilogram. Now after the collision, they collide with each other. This one is moving 3 meters per second, and this one is moving 4 meters per second. After the collision, the object moves with 1.2 meter per second. Now P initial x equal to P final x, and from this one here, m1 v1 initial plus m2 v2 initial equal to m1 v1 final plus m2 v2 final. Now this one is equal to 0. 5 times 4 minus 4 times 3 equal to m2 v2 final x. In other words, v2 final x equal to 8/4 or 2 meter per second. P initial y equal to P final y. In other words, now P initial y it's equal to 0 because it has no initial components on y, which is 0, equal to m1 v1 y final plus m2 v2 y final. You substitute the numbers, you will get minus 5 times 1.2 equal to 4 v2 y final. In other words, this one here, minus 6/4 equal to v2 y, or v2 y equal to minus 1.5 meter per second. Now v as a vector equal to 2I minus 1.5 j, and v the magnitude equal to 4 plus 1.5 square, because it's 2 square, and after all v will be equal to 2.5 meter per second. A 4 kilogram mass initially at rest on a horizontal frictionless surface. It's struck by a 2 kilogram mass moving along the x-axis with a speed of 8 meter per second. After the collision, the 2 kilogram mass has a speed of 4 meter per second at an angle of 37 degrees. From the positive x-axis, what is the speed of the 4 kilogram mass after the collision? Now in this case here we have an object 2 kilogram is moving with speed equal to 8 meter per second, collides with a 4 kilogram object initially at rest. After the collision, the 2 kilogram object is moving with speed equal to 4 meter per second and making an angle 37. So this one here, it's 4 meter per second. From the positive x-axis, what is the speed of the 4 kilogram mass after the collision? P initial x equal to P final x. So m1 v1x plus m2 v2x equal to m1 v1x final, this initial, plus m2 v2x final. Now the second object initially at rest, assuming this is m1 and this is m2, and you substitute the numbers, 2 times 8 equal to 4 cosine 37. This one here, the x component, plus 4 v2x final, and from this one here, v2x final equal to 2.4 meter per second. Now from the y component of the momentum, initially y, p final y, then m1 v1 initial y plus m2 v2 initial y equal to m1 v1 y final plus m2 v2 y final. Now again, this one is equal to 0, no y component for the second particle or object, and no y component for the first object. So 0 equal to m1, which is 2 times 4 sine 37. The y component for this one, it's 4 sine 37 plus 4 v2 y final, and from this one here, v2 y final equal to minus 1.2 meter per second. V, after all, as a vector equal to 2.4 I minus 1.2 j hat, and V, the magnitude, equal to, or the speed, equal to square root of 2.4 square plus 1.2 minus square. V, after all, will be equal to 2.7 meter per second. At an instant when a particle of mass 50 gram has an acceleration of 80 meter per second square in the positive x direction, a 75 gram particle has an acceleration of 40 meter per second square in the positive y direction. What is the magnitude of the acceleration of the center of mass of this two-particle system at this instant? Now, to calculate the center of mass acceleration, center of mass, we have to calculate the A center of mass x equal to m1 a1x plus m2 a2x over m1 plus m2. Now, the second particle has no x component, which is 0, this one here, so 0.05 times 80 divided by 0.125 or 32 meter per second square. Now, AY center of mass equal to M1 A1Y plus M2 A2Y divided by M1 plus M2. Now this one is equal to 0. You substitute the numbers. 0.075 times 40 divided by 0.25 or equal to 24 meter per second square. So A, after all, will be equal to square root of ax square, so 32 square, it's 1024, plus ay square, 24 square, which is 576, or 1640 meter per second square. At an instant when a particle of mass 80 gram has a velocity of 25 meter per second in the positive y direction, a 75 gram particle has a velocity of 20 meter per second in the positive x direction. What is the speed of the center of mass of this two-particle system at this instant? Again, the center of mass at x equal to m1 v1x plus m2 v2x divided by m1 plus m2. No x component for the first particle, And after all, 0.075 times 20 divided by 0.155 or 9.7 meter per second. Now, the center of mass y equal to m1 v1y plus m2 v2y divided by m1 plus m2. This one is equal to 0, and after all, it's 0.08 times 25 divided by 0.155, which equal to 12.9 meter per second. V, or the final speed, is equal to square root of 94.1, which is 9.7 square, plus 166.4, which is 12.9 square, and V will be equal to 16.14 meter per second. Three particles are placed in the XY plane. A 40-gram particle is located at 3 and 4 meters, and a 50-gram particle is positioned at -2 and -6 meters. Where must a 20-gram particle be placed in such a way the center of mass of this three-particle system is located at the origin? Now, the center of mass, X center of mass, equal to 0, and Y center of mass equal to 0. Now, let's graph the situation. Now, this is 40 gram located, assuming that this is 3 and this is 4. So this is 3 and 4. Now, for the second one, the 50 gram is located in -2 and -6, assuming that is -2. Again, this is a rough graph. -6, it should be somewhere here, and this is 50 gram at position -2, -6, and where a 20-gram particle should be placed in such a way the center of mass of the three-particle system is located in the origin. So X center of mass equals 0, Y center of mass is equal to 0. We would like to find where we should place a 20-gram object. So X center of mass equal to M1 X1, M2 X2, M3 X3 divided by M1 plus M2 plus M3. Now X center of mass, it's given equal to 0. So 0.04, because we have to convert it into kilograms, times 3, the X position, plus M2, it's 50, which is 0.05, times the position, it's -2, the X position, it's -2, plus, and 20 grams, it's 0.02, and we have no idea about its position, so let's keep it X3 divided by 0.04 plus 0.05 plus 0.02. You simplify this one here, you will find X3 equal to -1 meters. Now Y center of mass equal to M1 Y1 plus M2 Y2 plus M3 Y3 divided by M1 M2 plus M3. Now let's substitute the numbers. So 0.04, and the Y position for the first object, it's 4 plus 0.05, the Y position, it's -6, plus M3, it's 0.02, and again we don't know Y3 position, divided by the total mass, 0.04 plus 0.05 plus 0.02. in such a way, if we solve this one here, y3 will be equal to 7 meters. So the position for a 20-gram object should be placed x and y, in this case, in -1 and 7 meter. A 3-kilogram stone is dropped from 39.2 meter high building. When the stone has fallen 19.6 meter, the magnitude of the impulse it has received from the gravitational force will be. Now, when we drop an object 39.2 meters, in this case here, and this is 3-kilogram object, when this stone falling 19.6 meters, the magnitude of the impulse will be. Now, impulse actually it's equal to delta P, or P2 minus P1. Now, P2 it's M V2 minus M V1. Now, V final square equal to the initial square equation of motion minus 2g delta x. So the final square equal to, now initial, this one is equal to 0. So minus 2g times 19.6 minus 39.2. And v in this case will be equal to square root of 392, or v equal to 19.8 meter per second. So the impulse will be equal to 3 is the mass of the object times 19.8 minus the initial momentum, it's 0 because it has 0 velocity, and impulse will be equal to 59.4 Newton second, or kilogram meter per second. A 0.28 kilogram stone you throw rises 34.3 meter in the air. The magnitude of the impulse the stone received from your hand while being thrown is. Now let's calculate the impulse right here, equal to P2 minus P1, and you substitute the numbers. It's 0.28 times 0 plus 0.28 times V. Now we need to find how much V in this situation here. So V final square equal to the initial square minus 2g delta y. Now at the maximum height, this will be 0. So V will be equal to square root of 2 times 10 times 34.3. And V will be equal to 26.2 meter per second. Impulse, after all, will be equal to 0.28 times 26.2, and this one here 0 because it's multiplied by 0. So it's equal to 7.3 Newton seconds, or kilogram meter per second. That's it. Thank you for watching.